Welcome everyone to our final lesson in Unit 4. Today's lesson is going to be on artificial transmutation, and we're going to talk about how we create the transuranium elements. And those are going to be the elements beyond uranium, which is atomic number 92. So we'll take a look at how those are created. Today you're going to be able to complete nuclear equations and predict missing particles from nuclear equations. And you will also be able to compare and contrast fission and fusion reactions. So we'll take a look at those towards the end of our lesson here. So artificial transmutation is when scientists create new elements, specifically the ones that are beyond atomic number 92. Uranium would be the last naturally occurring element that we have here on Earth, and all the elements beyond atomic number 92, beyond uranium, would be artificially created. And all of those elements are going to be radioactive, meaning they don't have one single stable isotope. And the device that's used to produce these elements is called a particle accelerator. And we'll take a detailed look at what one of those devices looks like and how they work. But all of these elements are going to be created using that particular device. How exactly is it done? How exactly do we make an element bigger than uranium? Well, we need three ingredients. One, we need a sample of target nuclei, usually a heavy one, a heavy element that we can use to try and combine with something else to produce a heavier element beyond what we started with. And we're going to do that with the assistance of a particle bullet, which has to have a charge, and we'll learn in the video exactly why, which is generally going to be a positive charge, like an alpha particle, which is a charged helium atom, or some other nucleus as well. But electrons can also be accelerated too. The key here is that the particle has to have a charge, because we're going to accelerate it in an electric field. And the particle accelerator is going to make this bullet move fast enough, really a velocity close to the speed of light, and it's going to collide with that target nuclei, the heavy nuclei that we started with, and change it into different elements. Now the particle accelerator, as I said, is going to use an electric field, but it's also going to combine that with a magnetic field. So we get an electromagnetic field that's going to be used to accelerate these charged particles to speeds that are close to the speed of light. Neutral particles, however, cannot be accelerated in the particle accelerator. So neutrons or gamma rays are not going to be able to be accelerated using this particular device. We'll take a look at a little bit behind the particle accelerator.
One of the grandest scientific tools ever made by mankind is called an atom smasher. And I mean literally grand. The biggest one ever built, the Large Hadron Collider, or LHC, is a ring with a circumference of about 18 miles. That's more than the entire length of Manhattan. So what is an atom smasher? It is a device that collides atomic nuclei together at extremely high energy. The most powerful one scientists have ever built can heat matter to the hottest temperatures ever achieved. Temperatures last seen a trillionth of a second after the universe began. Our accelerators are full of engineering superlatives. The beam-containing region of the LHC is a vacuum with lower pressure than what surrounds the International Space Station and is 456 degrees Fahrenheit below zero, colder than the temperature of deepest space. A previous accelerator sitting in the LHC tunnel holds the world record for velocity, accelerating an electron to a speed so fast that if it were to race a photon of light, it would take about 14 minutes for the photon to get a lead of about 10 feet. If that doesn't impress you, remember the photon is the fastest thing in the universe. It goes about 186,000 miles per second. So how do these subatomic particle accelerators work? Well, they use electric fields. Electric fields make charged particles move in the same way that gravity will pull a drop baseball. The force from the electric field will pull a particle and make it move. The speed will continue to increase until the charged particle is moving incredibly fast. A simple particle accelerator can be made by hooking two parallel metal plates to a battery. The charge from the battery moves onto the two metal plates and makes an electric field that pulls the particle along. And that's it. You've got a particle accelerator. The problem is that an accelerator built this way is very weak. Building a modern accelerator like the LHC this way would take over 5 trillion standard D-cell batteries. So scientists use much stronger batteries and put them one after another. An earlier accelerator used this method and was about a mile long and was equivalent to about 30 billion batteries. However, to make an accelerator that is equivalent to 5 trillion batteries would require an accelerator 150 miles long. Scientists needed another way. While electric fields will make a particle go faster, magnetic fields make them move in a circular path. If you put an electric field along the circle, you don't need to use miles of electric fields. You can use a single electric field over and over again. The beams go around the circle, and each time they gain more energy. So very high energy accelerators consist of a short region with accelerating electric fields combined with a long series of magnets that guide the particles in a circle. The strength of the magnets and the radius of the circular path determines the maximum energy of the beam. Once the beam is zooming along, then the real fun begins, the smashing. The reason physicists want to get those particles moving so fast is so they can slam them into one another. These collisions can teach us about the fundamental rules that govern matter, but they'd be impossible without the feat of engineering that is the particle accelerator.
Now, with this idea in mind behind how particle accelerators work, we're going to take a look at how we can apply this to some different nuclear equations so we can determine reactants and products of these different artificial reactions. And there's a process that we're going to follow to do this. First step, one of the products is going to be unknown. So we're going to kind of complete these like we've done some of our other missing step equations in our reactions previously this year, and try and determine what one of those missing products is going to be. And we do this by using the law of conservation of mass. So we're going to add up the mass numbers on the side where we know all of the particles and compare it to the one where it has the missing particle. So we'll add up the atomic numbers on the side where we know all of the particles. Remember, we're going to keep a conservation of mass. And then we're going to have to look up the element that we need on the periodic table or reference table O if it is going to be a particle as opposed to an element. So we might see a nuclear particle like a alpha particle or a hydrogen atom as well. We're not going to see any beta particles in these types of equations. So we'll do a couple sample problems together. This looks like a typical reaction. We do have a missing product X here. And in this equation, we know all of these starting materials. We know all of the reactants on the left side of the arrow. We have a nitrogen atom, we have a helium atom. On the right side, we have an oxygen atom and an unknown species. So we want to remember the conservation of mass. So the left side, we have a total mass of 18. We're adding up the 14 and the 4, our two atomic masses, to get a total of 18. And that's going to have to be conserved to the other side. Right now, it only has a mass of 17, which means X here must have a mass of 1, so we can have 18 balanced on both sides. We also want to conserve our nuclear charge. So on our reactant side, our left side, we have a charge of 9, 7 plus 2. And on the right side, we have a nuclear charge of 8. But we want a nuclear charge of 9, which means X must have a charge of 1. So now we use our periodic table and we look to see which element has atomic number 1. Remember, because that's what determines what element we have. And we can do that on the periodic table. You can also tell that from reference table O, and that tells us that X is a hydrogen atom. Sample problem 2. In this example, we again know both of our reactants and we're looking for one of our products. So we know all of the numbers, all of our masses on the left side of the equation, and we're looking for an unknown on the right side. So we use the law of conservation of mass and tally up our totals on the left side, and we'll compare it to the right. We'll start with the atomic mass. On the left side, we have 27 from aluminum and 4 from helium. That's a total mass of 31. On the right side, we only have a mass of 1. We want that to be 31, so X is going to have a mass of 30. Now we want to conserve nuclear charge. Left side we have 13 and 2 for a total of 15, but the right side doesn't have any nuclear charge. Right there we have only a neutron. That N, we can tell from table O, is just a neutron, has a mass of 1 but no nuclear charge, so that's a neutral nuclear charge. The right side must have a charge of 15, so X must have a charge of 15. And in order to figure out what X is, we want to look that up on the periodic table, see what an element has atomic number 15. And this is going to be table O, but the periodic table, X is going to be phosphorus 30. Phosphorus has atomic number 15. Now we'll do a couple more examples here. Feel free to pause the video and complete these problems and check your work. Now for the first one, now we know, remember we want to start with the conservation of mass and compare those to both sides, both the atomic mass and the nuclear charge or the atomic number. In this case, we know everything on the right side or our product side. So we can start with our atomic masses. 6 and 4 gives us a total of 10. So we're going to want 10 on the left side. And 3 and 2 gives us a total of 5. So we're going to want 5 on the left side, which means we're going to want a 4 here. And we're going to want a 9 here. Looking this up on the periodic table, we get beryllium 9. Given the equation here, when the equation is correctly balanced, the particle represented by the X will be. So we'll start with our atomic masses. 14 and 4, we know everything on the left side, that's 18. And our nuclear charge is a total of 9. Comparing here, 9 and 8. We're missing 1 here. And 18 and 17, we're missing 1 there as well. So X must be a hydrogen atom. The next practice example, given this reaction, X is going to represent. Well, X is on the left side, so we're going to tally up everything on the right side. 78 and 1 is 79. 35 and 0 is 35. Which means for our atomic mass, this would have to be a 4, and this would have to be a 2. So X is going to be an alpha particle for a helium atom. Now we're going to take a look at 2 different types of nuclear reactions. You need to be able to compare and contrast between these 2 different types. And the 2 different types of reactions are shown here. And we'll talk about some specific details and particulars for each type of reaction. And the one on top here is a little bit harder to read. But to the right of the arrow, we have 3 products plus energy. So the only 2 reactants we have are that uranium and that neutron. And we're going to start with that reaction first. That reaction is an example of a fission reaction. And a fission reaction is going to take a large nucleus, in this case the uranium-235, and split it into 2 smaller ones. And if you think about how the particle accelerator works, we can't quite use a neutron to smash into uranium because it can't accelerate a neutron, but this reaction can happen in other ways, not just with the particle accelerator. So when this happens, this neutron essentially runs into that large uranium atom and splits it into 2 smaller ones, krypton and barium, and in the process releases 3 other neutrons. And these neutrons can go on to split other uranium-235 atoms. And the biggest thing with this reaction is the amount of energy that it produces. Now this reaction can take place at any temperature or pressure. It doesn't require any large temperature or vast pressures in order to happen. We currently use this in our nuclear power plants to produce electricity using a different isotope of uranium, which is going to have to be mined from the Earth. It is very abundant in the crust of the Earth, as we know. Now, these types of reactions produce thousands of times more energy than other types of chemical reactions. So these are much greater. These nuclear reactions are thousands of times more energy dense than a chemical reaction, at least in this case in regards to fission. The only problem with this, or at least one of the problems, potentially the only problem, is that it does produce radioactive waste. So when this reaction occurs in a power plant, over time, the power plant does generate radioactive waste that has to be dealt with. And as we know from radioactive decay, this waste can take sometimes thousands and tens of thousands of years to decay into something that is stable. And during that time is emitting high energy particles in the form of radiation that can be damaging to living things. The next type of reaction we'll take a look at is a fusion reaction. This one is a little bit more interesting. It's a little more, or a little less known, I should say, and not fully practiced, really, not in the way that fission is. And this reaction is going to take, it's the opposite of fission. It's going to take two smaller nuclei, two hydrogen atoms, and it's going to combine them into a larger nuclei. In this example, that larger nuclei is a helium atom. And just like in fission, it's going to produce an enormous amount of energy. And it's actually going to produce much more energy than a fission reaction. One of the issues with this reaction is that it requires temperatures of millions of degrees, which we know on Earth is extremely difficult to achieve, and enormous pressures. This is a reaction that's occurring on the sun, where there is temperatures of millions of degrees and enormous pressures from the gravity and the matter on the sun. So this reaction occurs readily in all of our stars due to that reason. Now, this reaction produces millions of times more energy than chemical reactions, much more than a fission reaction. So fusion is significantly more powerful than fission, but it's much harder to achieve because of those temperature and pressure requirements. What's nice about fusion is that it doesn't produce essentially any radioactive waste. We produce helium from that reaction as opposed to potentially other radioactive particles or radioactive isotopes that then take time to decay to something stable. These two types of reactions are similar in that they use the mass defect to destroy a little bit of mass to produce this enormous amount of energy. But they are slightly different in their requirements to get the reaction started and in the ways that they produce. And we're going to take a look at here on the simulator exactly what these reactions can look like, both singularly as well as in a reaction. Now we'll take a look here quick at a single fission reaction. We have a unstable uranium-235 nucleus, and we're going to use our little gun here to shoot a neutron at this atom. And we'll kind of see what happens. It absorbs that neutron, goes to a higher energy level. It splits into two daughters. Those are the two smaller nuclei, and then we see three neutrons that are released from that reaction. And these neutrons that come out of it here, those three, like we saw in our sample equation, those can now move on to collide with other uranium atoms. And this kind of becomes a chain reaction. So the more that we put in here, let's say we fire one neutron at this one uranium-235 atom, it's only one bullet, but then we get three more that are released from one, combining with three more, and so on. It just depends on how dense these radioactive isotopes are in this particular vessel. So we'll shoot it at one, and we can kind of see the chain reaction that happens here. Now this is really only with 50 nuclei in a little simulator, but if you're looking at using uranium rods in a power plant, we might contain trillions and trillions and trillions of atoms. And this reaction can get pretty aggressive. And we can put other different types in here. And you can see that triggering one and releasing these other 3 bullets creates a pretty massive chain reaction that sometimes can get uncontrollable. And in a nuclear reactor, that's what's known as a meltdown. Now, this is a little example of what a core of a nuclear reactor might look like. And we'll talk about some of the specifics of how this works. Now, in this vessel, we have 6 different chambers that contain uranium. Now, this might be what they call uranium fuel or uranium rods that would sit vertically inside these reactors. And this whole reaction is moderated with these control rods, which we can move in and out of this vessel, which is going to help us to control the rate of the reaction. Surrounding this vessel is water, and water is used to cool the reaction, to keep it from essentially melting down and getting too hot. And that water, as it surrounds this reaction, heats up, produces steam. That steam turns a turbine, and we generate electricity. So just like in any or most types of electricity production, we are trying to heat water to produce steam, and that steam can turn a turbine. So this reaction has to get started, and we'll take a look at this a couple different times so we can see some of the things that can happen here. Now, there's 2 graphs here. One is power output, and one is total energy that's produced. There is a certain amount of potential energy within all of this fuel inside the reactor. If we were to react all of it, it's going to produce a total amount of energy. The power output is per second. And if this gets too high, then we can have a meltdown. So this kind of has to be moderated with these control rods. So I'm going to start here with these poles. Let's go about halfway out. We'll fire a neutron and we'll kind of see what happens. We see our reaction start up here. We can monitor our temperature. And this is mostly occurring over here. And we start to see some of the neutrons starting to move into some of the other chambers. And our power output is kind of low. But if we open this up and expose more of that fuel, we can see our energy increasing as more of that fuel is exposed. And if this got too hot and we wanted to close this, we could close these down and the power output falls all the way down. Now, if we keep this fully open and we fire a neutron and this reaction is allowed to just occur at its own rate, uncontrolled, the temperature here, depending how quickly this happens, will start to rise. We can see our power output per second staying pretty high. And as our temperature gets all the way up to the top, which it may or may not happen, we would essentially achieve a meltdown. So the water has to moderate the temperature of this reaction, and we can control the rate of that reaction with these control rods as we insert them to block the fuel from being exposed to more neutrons or fast-moving neutrons to start the reaction. So that's the basics of a nuclear reactor in a nutshell. If you guys have questions on fission or fusion, make sure you write them down and come see me to get your questions answered. Have a great day.